Well, good morning. Good morning. Glad to see everybody here. I hope some of you made it to the presentation this morning. I'm going to not repeat, hopefully, a whole lot of that stuff. What I want to talk about today in this session is more classroom practice. You know, we're down and dirty. Like, what do we do? You know, the session this afternoon, I'll be talking more about the stuff. The tools, what to buy, you know, the sort of shopping list kind of stuff. Even though I said shopping stuff, the most important thing is one of the important things. But what I want to talk about today here is the kinds of scaffolding, the kinds of challenges you can give students that really kind of propel these maker movement kinds of experiences in the classroom. So, as you heard in the keynote, I co-authored a book called Invent to Learn. And we're going to be doing a book signing, I think it's 2:30 this afternoon in the makerspace. If you've been to the makerspace, hackerspace, they've got some amazing stuff there to play with. And I think that you should definitely go there, add to the crowdsourcing sculpture that's going on. And again, anything I say is on our website, inventtolearn.com. There's a resource section. There's a list of stuff to buy. There's all kinds of really interesting resources. And you send an email to friend@inventtolearn.com, you will be automatically subscribed to our Invent to Learn newsletter. So, I think it's always nice in the classroom to start out with models that we know, models that we're familiar with. To me, the biggest model that matches the maker movement is project-based learning. The nice thing about project-based learning is there's tons of resources, there's tons of research. If people are saying to you, well, how do we know that kids learn by hands-on? You can say, I've got, all kinds of research from Harvard, books written about project-based learning. But I think project-based learning can learn a little bit from the maker movement too. There's other models like Genius Hour. You guys heard of Genius Hour? And design thinking has come up a lot lately. So Genius Hour is this idea that in some companies like FedEx or Google, they give their employees 20%. So it's called FedEx time, 20% time. 20% of the employee's time supposedly is available for the employee to work on projects that are sort of in the company's interest. I'm not a big fan of using business models for the classroom. I think it's an interesting recruiting tool to tell employees that they'll be able to work on projects of their own interest. And I think Genius Hour, if you can only spare like an hour on a Friday afternoon to do more open-ended things, hey, it's a great way to get started. But I think project-based learning as a whole can be every hour. It doesn't just have to be like 1 hour a week. Design thinking is another new model. It's from IDEO. It's a company. They're aligned with the Stanford Design School. It's a way to do project design. So there's some really interesting tools and templates if you look on their website about the design process. However, to me, Peppersian constructionism, Seymour Papert's idea of constructionism, is really solidly rooted and supports this making in the classroom. And that combined with project-based learning, I think, gives you a really good model for how to bring this stuff to life in a classroom. Whereas design thinking, and design thinking in particular, to me, seems narrow. Because product design isn't the only kind of design you do, right? You don't always have an audience. You don't always need a marketing plan. You may say, today I want to explore. Today I want to see what these materials tell me, like an artist does when they start a sculpture. They don't have to have a marketing plan for a sculpture, right? That's not artistic. That's not the way artists work. Nor a lot of writers. You hear a novelist talk about their writing, they often say, the characters speak to me. The materials speak to them as they're writing. And the plans change. So I find making in the classroom to be, well, for one, the right verb for me. It's not thinking, it's making. That's where to start. I think the nice thing about making and project-based learning together is that they complement each other really well. I think making brings this idea of bricolage, which is a French word that means tinkering. And it's an absolutely fabulous word because it kind of has this also very artistic sense of reusing materials and having surprises happen. And the idea that time is important. Project-based learning can't be scheduled. We need to relax our schedules. We need to lower the stakes on assessment. We need to trust the process. And I know that that's a tough thing in school. So we'll talk about time a little bit later too. I think we also need to move kids in project-based learning away from the teacher as being the expert who knows everything. Too many step-by-steps, too much instruction stops the learning process. It stops the kids from thinking and starts them thinking, what does the teacher want me to do? Now, this doesn't mean unguided, right? A lot of people think, oh, you're talking about discovery learning. The kids are just going to kind of, wander through the fields with flowers in their hair, and the Pythagorean theorems will just, emerge out of it. And people have this really weird feeling about teaching. It's either like they're all sitting in rows and quietly while I lecture, or not, the teacher does nothing and the kids just discover. I mean, obviously, there's a huge range in between. It's hard for people to understand that teaching isn't talking, right? Because when you're not a teacher and you walk in a classroom, if the teacher's not doing anything, well, what do you think? You're not doing your job, you're not teaching. But a teacher who's guiding, a teacher who's creating an environment where kids are naturally running across the big ideas and then helping them, propelling them along the way, that's a huge professional accomplishment and an art. So in a lot of these instances, it causes us to rethink. When we do project-based learning, when we do making in the classroom, we start to question, like, these schedules just aren't working for me. How come math and science are separate subjects? Now, you can't change everything. Look, if you're building a new school, that's great. But most people aren't. Most people are working within an existing system. I don't think there's one place to start. It's not like you can say, okay, first we're going to have double blocks and then everything else will change. In a lot of schools, the making comes first. What I see maker schools doing is anything they can get to as a first step. Because there's never perfect, right? There's never the perfect budget, there's never the perfect time, there's never going to be agreement on everything. You're never going to get all your ducks in a row. And when you wait for that, it just gets delayed and delayed and delayed. So a lot of schools try whatever they can. It's an after-school program, it's during lunch, it's a maker day on Saturday, it's, just getting started with things, because when you show people what kids can do with these fantastic materials and tools, then they'll start saying, well, how can we get this into the classroom in other ways? And then if you can get it in for an hour, make it 2. And if you can get it in for 2, make it a day. You can get it in one subject, all of a sudden teachers start saying, I need more time for math. Well, I need more time for science. Well, why aren't we doing this together? Why are we doing them separately? So questioning those things takes time. It's always better if you have supportive leadership. Everything is. But showing people what kids can do, I think, goes a long way towards convincing people that these steps are possible. Another thing to rethink is the stuff. In a lot of schools, we have things for the students. Everything's kind of a kit. You have a kit for science, and you have your textbook for English, and you have, everything's sort of predetermined. Whereas if you think about what a good kindergarten classroom looks like, it's kind of full of things that the kids might be able to access for any reason. If we can get more stuff available for kids and let the kids have time to get good at using materials, then they'll be able to solve problems in new ways. Maybe ways that we didn't even expect them. So I'm going to talk about stuff, even though I said the shopping isn't the most important. I think these materials are new and you can think of them in new ways. So when I talk about the top tools of the maker movement for classrooms, you heard this morning, I have my 3 game changers, but I also have a lot of other things, a lot of electronics materials, and traditional materials too. Legos are fantastic. Cardboard is fantastic. You don't need to throw anything away. You need to figure out how to use what you've got and hybridize with these new materials. So when we're looking at the kinds of spaces that make for good making, we don't want to have a sterile classroom with desks all in, rows of desks and, nothing on the walls, obviously. We want to have spaces where kids can have access to materials and can move, can change the space to make it more flexible. Anytime you have the ability to make a space more flexible, to provide the kids with display areas, storage, that's definitely, something you want to do. You talk about like baby talk, right? You want materials that let kids do something quickly, and then you can say, well, what can you do next? You can challenge them. They can raise their game. They can get better at things. We don't read babies walking rules or grammar rules. We let them walk. We let them talk. And if they fall down, we help them stand back up again. If they say something, that's the wrong plural formation, we don't say, no, you never add the ES to the P, We just respond to them in a normal conversational manner. And in that way, the human brain is wired this way. In that way of using language, they become better at it. You also want to give kids a lot of aesthetic choices, because I know we're talking about putting the A back into STEM, right? We're putting the arts back into science, technology, engineering, and math. I think schools have artificially extracted the arts out of science and mathematics in a lot of ways. And when kids have access to materials and have the time and projects they care about, they can put their own aesthetics into it. That's, again, a very natural human impulse. The great science educator Eleanor Duckworth says that if materials are slim, the only questions likely to be posed are the teachers. A lot of times, in the interest of time, we give the kids 2 pipe cleaners, 2 googly eyes, one this, one that, and paper plate, and we know exactly what they're going to make. In fact, we even may tell them, we may give them a picture of exactly what we want them to make. Well, guess what? There's no out-of-the-box thinking. You've told them what to think. And we've done a good job of training kids to wait for us, right? Where's the handout? Where's the step-by-step? How many pages? How many, kids are doing great in school. They've learned that lesson. And a lot of maker teachers say, my kids, they don't know what to do. And it takes time to unlearn. Now, I had an 8th grade history teacher who used to tell us, whenever we'd say how many pages and everything, he would say, you cook the turkey till it's done. It's like, oh, great. And it's especially frustrating for your good students who've really learned the game. They know what to do. They are waiting for you to tell them, because you've always told them how to get an A. And if you don't tell them, they're confused. And then their parents come in and say, how many pages, how many bullet points, how many sound clips, needs to be in the project. And then you know who's really doing the project. But you have to untrain your kids. If you're planning to do more maker stuff, more project-based learning, you have to give them time to unlearn that you're not going to help them. Now, it doesn't mean you're mean, right? In our book, we talk about 2 kinds of frustration: mouth-up frustration and mouth-down frustration, right? Mouth-up frustration is like, I'm going to solve this problem, I'm going to tackle it, I'm going to figure it out, I'm going to climb Mount Everest, and it's not working, well, maybe tomorrow, and you're excited about your challenges. Mouth-down frustration is, this is impossible, I don't know what to do, my hard drive has crashed, that's not good frustration, right? And a teacher can alleviate those kinds of frustrations. But you want kids to have some of that mouth-up frustration, where they don't get an instant answer to every question that pops into their heads, but they have to actually grapple with things. So as far as stuff goes, I can tell you I showed you the video of the Makey. I'm not going to re-show that video again. It's one of the things I highly recommend for everyone starting out on a maker project. One of the reasons are it can go from very young to very advanced. You can do all kinds of different things, because essentially it's just an interface. It's kind of an interface accelerator. So you can work on the interface part, you can work on the computer project part. There are all kinds of guides online. There are brilliant videos that go everything from theater arts, like having interactive costumes, where if one actor touches another, because they're both like wired through their costumes, you just need long USB cables, where if you touch another actor, a sound effect or a light effect plays, to to history, to t-shirts that could be like the digestive system and you touch it and the Scratch program plays, you know, biology facts. There's no software to install, it's not messy, it's not dangerous, it doesn't need batteries, and it's really cheap. And Makey costs $50. I wish I was getting commission on Makey, but I'm not. So I really do love this tool. And there's actually, it's actually hackable. There's an Arduino microcontroller on the back of it. You can go in and hack that and use it just like an Arduino. So there's a place for kids who say like, okay, now I've done everything I think I can do with it. Where do I go from here? I love the where do I go from here. You know, you do want the baby talk, you do want the low threshold, but you also want a high ceiling. You don't want something that kids do at once and they've mastered every nuance of the tool or software. You know, it may be harder. Some things are actually difficult to use. You know, let kids get good at things. That's a good thing. Having fluency for over a complicated process or project is how you learn. So there's lots of different makey projects. This one, for example, is a wind chime. You can see that it's kind of light, but this is a liter bottle with aluminum foil strips down the side, alligator clip to the makey. The makey is plugged in the computer. The computer is running a keyboard program. So that this clip might be, say, a space bar. And when you touch that with the drumstick covered in foil, it makes the connection. It plays, say, a space bar. The computer program says, aha, space bar is middle C. So this is a wind chime that plays this keyboard, any of these, you know, anything that it touches, but it could just as easily be a recording of her voice or animal sounds, or I had a workshop last week where they were doing burping and farting, middle school teachers. So, but that's, you know, it's up to the kid. This one is that t-shirt like I was talking about. So this is a t-shirt where there's regular sewing snaps. They're metal, right? So they're conductive. So if you're grounded, when she touches the snap on her shirt, which she's drawn the digestive system, now this other shirt is the circulatory system, so they were a pair. This is a team of teachers working at our Constructing Modern Knowledge conference. When she touches the snap, it lights up an LED and it triggers the makey to show there's a little hamburger going down the digestive system, and it gives you facts about digestion. So this is a Scratch program that's triggered, say, maybe this snap is attached to the space bar, this snap is attached to the up arrow, and each one of those in the Scratch program triggers a different part of the animation. This is another project by Josh Berker, who's a really inventive teacher. We're working on a book. He's working on a book for our publishing company with a lot of these kinds of really fun projects. This is an operation game. You guys remember the operation game? You have to like get the organs out of your patient without touching the sides. Well, these are copper foil covered chopsticks. The copper foil lined little holes. When the chopsticks touch the foil, it connects to the makey, triggers something in the Scratch program. So you can probably see that if you had teams of kids, maybe someone work on the computer, maybe they would make animations, or the patient would say ouch, or keep score, or whatever they wanted. Josh does another interesting thing, he's a resource teacher at a K-5 school. So he has a team of 5th graders, his highest grade, who helps him create the basic. They prototype everything. So when he comes into a classroom, the 5th graders have prototyped these boards, so they know if they need to hot glue gun parts, they know if, you know, maybe they need to create the chopsticks because that's too hard for the 2nd graders, but the 2nd graders can do other parts. So he has his 5th graders as a prototype tech team, helping him with these things. And then he can take his cart, wheel it into a 2nd grade classroom, and in 42 minutes or whatever the teacher tells him, they can do some pretty amazing projects, just with a little prep. This is also another project of Josh's. This is a software program called Turtle Art. So Turtle Art is Scratch-like. It's a subset of Scratch. It does beautiful two-dimensional geometric drawings. So in his school, they were studying Islam and different religions and Islamic tile patterns. So every student made their own tile pattern in Turtle Art. Now, before the maker movement, that would have stopped there. You could print them out, you could put them on the walls, but now you can do something else with it. So Josh had every student save the program, import it into Tinkercad. Tinkercad is a 3D modeling program that's available online. It's by Autodesk and it's free. So computer-aided design, CAD programs for little kids. Look how easy this looks, right? That's totally doable. You're just dragging shapes onto a plane. Oh, by the way, there's a coordinate grid. Do you want your kids to know about coordinate grids? Well, yeah. Well, now they have to. They have to figure it out. So you import the graphic and you extrude it. You grow it. So now it's got a third dimension. When you print this out of a 3D printer, it looks like this. With these stamps, you can test your stamp out in Play-Doh, stamp fire in clay. The fire tiles can be painted by the kids, and now you have a classroom set of tiles that connect culture, geometry, a beautiful, collaborative effort. And I love these kinds of projects that branch over lots of different subject areas like that. So where do you find out things like this? How do you know Josh? I met Josh on Twitter, right? I know people think that Twitter is all about Kim Kardashian like tweeting what she's wearing. I know. Seriously, if you follow certain hashtags, and some of you are probably doing this already, I know you are, you can find the most amazing things and the most amazing people. There are websites, if you go to the inventorlearn.com website, there are websites that have people have projects. But I'm telling you, if you want to be in a continuing conversation where people will actually talk back to you and answer questions, the Twitter hashtag MakerEd, so you use the #, it's called a hashtag, so if you use a tool like, I use Hootsuite to follow my Twitter conversations, and I just tell it, show me everything where someone attaches hashtag MakerEd to the end of their tweet, and I find the most amazing people and the most amazing projects. There's a couple of Google groups. You don't have to copy that URL down. That's all on the Invent to Learn website, where people are sharing and doing things. There's a couple of programs. I'm working with the Stanford Fab Learn Fellows. They've got 18 educators from all over the globe, people working in maker spaces in Kenya, in South America, and in the US, and museums and schools, all contributing to databases that are going to be more and more available to you as teachers to say, what do I do with my 3D printer? So, in our book, we spend a couple of chapters talking about the idea of prompts and challenges as a different way to think about lesson planning. Now, a lot of people lesson plan project-based learning lessons backwards, right? You start with the objectives, you do the backwards design, and then you create an environment where the kids are going to learn those particular objectives, and then you set up an inquiry question or driving question or something. And I think there's another way to do it, is not backwards, but frontwards. If you have materials you're using, like 3D printing, where you know kids are going to be grappling with certain kinds of objectives, I don't think you have to start from back. I think creating the prompt is the most important part. And then an interesting prompt will challenge the kids to build something that you can then go and say, oh, look at all the standards I can check off. So I think this is an interesting jigsaw in talking about classroom planning. You can do some backwards design, you can do some frontwards design with really interesting prompts and challenges, if you have the materials to back it up. So I'm going to show you three projects. So this is an elementary school project. You'll have to imagine, you can hear all the chattering going on. These are called jitterbots. It's essentially just an off-center motor. So you build any kind of little platform, put an off-center motor on it, and it'll just start doing a random walk. This is middle school. So this is the one I showed downstairs. The sound's not working. So this is a stuffed animal with an Arduino controlling it. So you have computer programming, you have control, there's motors and sensors. Well, there's no sensors in this one. There's motors inside of the elephant. And then this one is a magic 8-ball. So there's a real magic 8-ball. There's a mercury switch. There's, all these wires connect to the Arduino. The programming on the computer has been downloaded into the Arduino. So you can actually move this, and it will come up with different sayings, just like a magic 8-ball. Only You write your own sayings. You could have 8, you could have 80. You could have them in different languages. You could have, you could take that LCD display out and put in a sound system and make it speak. There's all different things you could do. So all 3 of those projects are from the same prompt, right? It's just your expectations are different, and the materials are different that you give. You don't give kindergartners an Arduino. It wouldn't work. So with appropriate materials and an interesting challenge, kids will do things that maybe you don't even know, you don't even expect. They could invent, they could deconstruct, they could reconstruct things. And this can work for elementary, middle, or high school. Just telling them, okay, what we're going to do now for the next hour, the next day, the next week, whatever the appropriate amount of time is we're going to hack a toy, or we're going to make a new toy. And the kinds of things that are appropriate if they know how to use the materials and they have access to the materials. So the prompt design goals are 3. Brevity, right? You want something they can fit on a Post-it note. You don't want to over-explain. Ambiguity. You don't have to tell them everything. Make it so that, you know what, if they invent a brand new toy that's well beyond what you ever expected, if they bring in a Raspberry Pi because their older brother had one and hey, they just learned how to use it, that's great. They've exceeded your expectations. And then the third one is the most controversial thing I'm going to say, is immunity to assessment. Right? You're all going, no, we have to give grades. I know you have to give grades, right? That's obvious. That's the way schools work. I would love it if I could just wave a magic wand and no one had to grade anything anymore, but that's not the way things are. So what I'm saying is not that it's ungraded. It's that you push your projects towards the project being the assessment rather than you being the assessment. So that the materials are giving you feedback, right? When that little stuffed animal, if he turned it on and nothing happened, the materials are telling him whether it's working or not. He didn't need to wait for a teacher to walk up behind him and say, oh, look, your stuffed animal isn't working, right? That's judgment. The materials told him whether it was working or not, and then you have to troubleshoot. So you go into this iterative cycle of troubleshooting and fixing without a teacher, without judgment, without a teacher demanding what the next step is going to be or anything. Now, as much as you can push that needle towards the project doing its own assessment, I think that's really important. What can you use prompts and challenges for? I think it's really limitless. Now, of course you can do typical curriculum projects. You want to teach biology, you want to teach fractions, you can create challenges around typical curricular subjects, but you can also do things like update a traditional project. If you have a school puppet show every year, why not see if you can electrify it? Use the Makey Makey to make the sets interactive. See if you can just take a step up with the things you already do. I hate throwing good stuff away. If you spent years tweaking a project to get it the right balance and the right tone, and the kids' projects get better every year, don't start over, right? Build on that. Community service, student interest, a lot of times, anytime kids get interested in anything, that says, of course, that they banned rainbow bracelets because we banned Pokemon and we banned, whatever kids get obsessed with. Build on those interests. There are 3D printers to print, there are 3D looms you can print for rainbow bracelets. There's mathematics, there's all kinds of things you can do. This is deconstruction, so this is an example of deconstruction. These kindergartners are drawing what's inside a measuring tape. Do you know why it springs back? Can you explain it? Can you draw it? It's an interesting step towards documentation, towards technical writing, to be able to use vocabulary that you're not used to. You wouldn't ask a high school student to do this in this way. You might ask them to explain what's in a measuring tape, but use the language of material science that we've been studying. What's the force of the measuring tape? How much force does it take to pull out? How fast does it pull in? Why does it do it? You know, if you can ask more precise questions and have tools that they can use to actually take measurements, predict, and analyze things, you can take essentially the same prompt from kindergarten to 12th grade. I mean, everyone does, you know, you have engineering week and you do the egg drop, right? If kindergartners are doing the egg drop and 12th graders are doing the egg drop, and essentially they're doing the same thing, you're missing a whole raft of math and science in between. The 12th graders should be able to measure how long it takes to hit the ground, should be able to predict how long it takes to hit the ground, should be able to create containers and explain why their container is more protective than, you know, the container they built last year. A kindergartner can just have a fun time dropping an egg, right, and making a mess. That's great. But we sort of lose that. We lose that continuum where I think it's a lot easier than we think. So here's an example of a project built around a curriculum area. At this school, the junior level, this is 11th grade project, is to build a museum. Every year, every student builds an exhibit for a museum, and every year has a different theme. So this year's theme was cancer biology. So every student in the 11th grade built an interactive museum exhibit that explained or showed some aspect of cancer biology. That's solidly in the science curriculum. It's what they teach. It's what they expect the kids to know. And the kids are doing something. Obviously, you can build machines, kinetic and potential energy machines. Show me what you learned in your science class. It's a lot different than doing it with paper and pencil. Some kids can do it with paper and pencil, and then you ask them to build something, and they won't get it at all. And vice versa. You know, so why not let all kids succeed? This is a project built on kids' interests. So the students at this school, this is James Deck's school. It's a girls' school in New York. His classroom, the kids learn about Arduinos, and they build a lot of things. So this is one of the projects. After they learn about the Arduinos, he says to them, make something that would, you know, improve someone's life. So these girls, this is New York City, so they have security cards they have to swipe to get into the building. And the girls said, one of the teams said, we think it's really impersonal. We think that when you swipe in, it should recognize you and give you a compliment. So they wanted to build a flatter box. So now this is a really ambitious project. And actually, it's impossible because they can't have access to this security system and modify it to like give a compliment when they swipe in. But the girls came up with a really clever solution. They built a box that sits on top of the security system, and with a light sensor, it just gives a compliment when the light goes to a certain level. So when you put your hand with your card in front of the box, it always gets a little darker. So it looks like you're swiping and getting a compliment, but it's fake. I'd say that's just as clever as actually hacking the security system. Well, which of course they weren't allowed to do. Now you may be thinking, okay, it's all science and math. What about history? What about English? This is a project in 8th grade. This is another culminating project to design a monument. A monument to someone who we learned about this year. So the idea behind it is, how do you represent history? So the students at the school have access to everything in the makerspace they have. They have laser cutters. This is one of the first makerspace schools. And but this project isn't about makerspace. It's not about laser cutting. It's about history. What does it mean to represent history? You know, when you're trying to talk about the life of Shirley Chisholm, I think that's what this one is. Are you going to put up a statue? How do you explain to people what she meant, what she did? Are you going to represent it literally or metaphorically? Are there going to be doves? What do people see when they walk up? What do they read about her? This is the act of being a historian. You know, I think that's crucial. I think we need to give kids experiences where they do as much of the real thing that real scientists and real historians do as possible. And there's a book by David Perkins. Anybody have read Making Learning Whole? It's an absolutely fabulous book. You have to read it. He uses the metaphor of baseball. He talks about having kids play the whole game. Because you know what this is, right? What game is this? Baseball, right? What game is this? Baseball. It's the same game, but obviously there's huge differences. You know, caring adults have gotten together and figured out how to make this game appropriate for kids, but they're still playing the whole game when they're not chasing butterflies. These kids feel like they're baseball players. They're getting the experience of playing baseball. And Perkins makes the obvious point that in schools we often do the equivalent of having kids spend 12 years learning baseball rules and inspecting bats and drawing the field, and we never actually let them play. And it's the job of teachers to figure out what's the whole game, what's the appropriate version of the whole game of being a historian, being a scientist, being a paleontologist that can work in your classroom. I think what's cool about the maker movement is a lot of these tools are a lot more accessible and a lot cheaper. The tools that real scientists, and the way that real scientists work, using iterative design. Because when you're inventing something new, you're not using the scientific process. The scientific process is an experimental process. The design process and invention process is completely different. The iterative idea of going back and doing something over again. And you know, I think save as is a huge part of this. The save as feature on your files means you get to do things without starting over, right? Computers are remarkable for helping you understand a design process where anything can happen and you can always undo. You lessen the risk, you lower the stakes. You know, you let kids make mistakes. Now, I'm not all about failure. I know failure is kind of a big, everyone's talking about, you know, first attempt in learning and we want kids to fail. I don't love that vocabulary. I get the idea, right? I think kids should have challenges, they should learn to overcome hurdles, they should, you know, develop all those kinds of persistence and habits of mind. I don't love the word failure because it's too tightly tied to the big red F. You know? I think that you can't ask kids, especially the literal, you know, the concrete age where everything is literal, you can't ask them to discriminate. Well, this, when I say fail, I don't mean this kind of fail, I mean that kind of fail. It's too tough. You know, if kids want to say, oh, that was an epic fail, that's cool, they are owning it. But for you to say, well, that was a failure, some kids are going to never be able to hear that any other way. I mean, we know research, right, that says that when kids get criticized for their handwriting, they hear I'm a bad writer. They just can't untie that vocabulary. When kids get told that, you know, they didn't finish their math test, or they didn't do the time test, or they didn't learn their multiplication tables, they internalize I'm bad at math. And I think in the same way, kids can internalize, you know, the failure. And the failure has devastating consequences. So I don't feel we can like use that word lightly. Now, there's lots of things that you can change in the classroom, like constraints. Constraints are good, right? Constraints, you give kids certain materials, they can't, you know, light things on fire. There's always constraints, right? I mean, engineering is about constraints. There's never enough money, there's never enough time, the soil is always too sandy or too soggy or too hard or too, you know, whatever. There's always something that you're constrained by. Constraints are the heart of creativity. And yet, I think teachers don't realize what power they have to make choices and give kids projects. Overly constrained, everyone's going to do cookie cutter. Under constrained, no one knows what to do. In between, there's a lot of leeway. And that's not the only thing. I mean, you have control over the directions you give, the assignments you make, how specific the rubric is. Are you showing them the A+ work, right? Are you saying, this is what you have to do to get an A? Or you can not show them at all. Well, what do? I don't know. Break it up. You know, there's a whole range in there. Now, I'm not saying you go from here to there. If only it were that simple, right? But in between all these things, I think there's a lot of leeway and a lot of control that teachers have over their environment. Something we don't often have control over is time. I know that's a huge problem. I know we try and save time wherever we can, but we've got to move on. You know, tomorrow is exponents, and the next day it's pronouns, and we just march through the curriculum. I think for a lot of kids, we just lose them. They're just always on the march, and they don't feel like they have time to do anything. I don't know how we sort out the time problem. What I do know in a lot of maker schools, they see it. They realize that they have to do something about it. It's not like a mandate. We're going to all go to block schedules and nobody knows why. That happens a lot. We're doing it because we see that the kids need more time. We see that the projects improve with more time. Scaffolding. So, there's tons of scaffolding we do for kids. There's lots of traditional ways we scaffold. We give them lectures, and we give handouts and textbooks, and we give them reference material, even though we know a lot of it doesn't work, right? Lectures don't work. We do it because we think it saves time. Where in fact, we're really spending a lot of time, if you're lecturing, having things go right over kids' heads because they got nothing to plant in it. They've got no experience. They don't even hear the words. I went online and looked at science. It took me about 5 seconds to find this scaffolding. This is a science experiment, right? Where every detail is laid out. And you see this stuff all the time. Is this really an experiment? This is not an experiment. This is, you're just trying to figure out what the teacher wants to see on the paper. Took me another 5 seconds to find this one. Can you guys read that back? How much turmoil does the science project cause families? It's funny, right? Why is it funny? Because it's true. How have we done this to ourselves? If it's true, we have to change it. This isn't science. We have to be brave and say, this is more close to what we're doing than our ideas. And if we're brave and we can get rid of things that are wasting time, we will have more time. I know that flipped classroom has been a big thing. Well, Stanford's doing a study now that really made me rethink a lot of that stuff. This is unpublished research. So this is a classic pre-test, mid-test, post-test. They read a text and then they work at a table. The table meant there's a bunch of interactive materials and they were working on a science project. You can see the kids who started the same, the ones who did the interactive stuff first did better on the mid-test, did better on the post-test. You might say, well, that's text. Kids never read what you give them, so video is better. Well, so they did video. Same thing. You show kids video, you have them read text before they even have an experience to hook it onto, it's just a waste of time. So there's more time you can save. Another Stanford research study really made me rethink what I was doing. They said, when you think you give out step-by-step recipes, right? People are going to go through the step-by-steps, and then once they get the gist of it, they're going to branch off onto making unique and projects that aren't cookie cutter. Well, this research is saying that's not true. That given materials and no instruction, people will do a wider range of things and go deeper into using the materials than ones who are given step-by-step instructions. I mean, it makes me rethink what I do with teacher professional development. If I hand out a step-by-step, am I doing a bad thing? I think asking questions about your own practice is always a good idea. I think there's a lot of interesting research. So I kind of thought about what my scaffolding rules are with teacher professional development. And when I give people prompts or challenges in professional development, I tell them what to do quickly. I do it all at once. I make it incomplete. I often show examples of projects that are half finished. Because what do people think when you show them some crummy looking puppet with LED eyes that's unfinished and the sides are, aren't stitched properly? They think, I can do better than that. And that's the goal, right? Not that they're going to copy everything you do. They're going to go farther. I like to do lots of project ideas, short prompts that people can choose from. Because when I know when adults walk into my professional development, some people will make a beeline and say, what's the hardest thing? And go right to that. And other people will browse. And other people will, you know, make a little something, or they'll check their email. And then when they feel comfortable, they'll move to something else. They'll move to something else. So having a grab bag of ideas and projects and materials available, and encouraging people to get off the email and to keep moving, I think is the way to go. But you don't want to stop the person who says, I want to do the hardest thing right off the bat. I think also we can think about it, scaffolding, in terms of grade range. Now, for example, this is a circuit theory idea. In basic circuit theory, the teacher provides just right information. You provide a coin cell battery, some LEDs, things that you know won't explode. You're choosing materials for safety, you're choosing materials for appropriateness, and your goals for the kids are essentially like aesthetics and just sort of getting the gist of things. Now, as you go up in grade range, you want to add. You want to ask, first of all, you want to push the kids away from you so that the expertise comes from each other and from the real world, not always you. Because if you've got a classroom of kids going, teacher, 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 that's just a bottleneck, for one. It's annoying, and a bottleneck. You want more materials, more choice, so that they can choose the wrong things. That means you have to have time for them to regroup and do it over. You want to introduce more, danger and failure, challenges. Now, you don't want the kids to blow anything up. You don't want to introduce, you have to understand what the limits of the materials are. Plus mathematics, plus design, plus iteration, and the advanced concepts you want kids to learn. So the transitions, I think, for secondary look like in real life, going from, say, centers to more of a maker space, making, increasing the amount of materials and increasing the amount of time kids have with things. You want to go from play to tinkering. Now, I think tinkering, people think of it as sort of being aimless, but to me, it's directive. It's iterative, but you do have a goal. You'd never want kids just fooling around, obviously. So that's the art of being a teacher, is to keep things in line, keep kids moving, make sure the ones who are fooling around get back to work, and you want to make what they're working on interesting. I think tinkering is a natural extension of play. And play is, it's a powerful learning thing for young kids. I think tinkering starts to take the place of play in older kids. And tinkering is the way real scientists and engineers work. When I worked on, I told you guys, I was working on the GPS satellite system. We did not know how it was going to work, and there were tons of things we did wrong, but there was a lot of stuff we did right too. And taking those, finding our way, taking the right things and building on them, learning from the wrong things, we tinkered our way to the final project, to the final product. Then we wrote the documentation, which is the way most things go. You want to move from challenges to engineering. Engineering is more formalized. Engineering has more math. You can add that simply by adding constraints, adding requirements for precision and analysis to what you ask the kids to do. I showed this in the keynote. I think measurement may be, if there was one thing that people take a look at differently in the classroom, it's measurement. And when you have interesting tools to measure with, all you've got is a ruler. There's not much you can do precisely. Kids should be using calipers. Kids should be using sensors. There's all kinds of new sensors that plug into Arduinos to collect real data from the real world. If you have probeware, maybe break that back out again. Kids should be dealing with data, not textbook data, because textbook data is always too pretty. Real data has all of a sudden the thing goes up to 10 million and you didn't expect it. What happened? Why? Is it bad data? Should I throw out the data point? There's lots of decisions that need to be made that are real world decisions when you work with data. So assessment, the big one. Everyone wonders about assessment. Now I said before, push the projects in a way that the projects are doing an assessment rather than you providing an assessment. I think standards are a part of this. If you're being held feet to the fire with standards, make sure it's not just the bullet points, right? the 4.7.8.2 students will learn to conjugate, blah, blah, you know. Because if you read the overarching language, it's extremely supportive of project-based learning. So if you're being held to the bullet points, you need to hold other people accountable to meet all of the standards, including the overarching language that says, explicitly calls the next generation science standards, which, by the way, written by scientists, go figure, call explicitly for engineering and meaningful assessment. The Common Core Maths says the problem should have real-world relevance, not simply like, you know, the kinds of textbook relevance where they, you know, make things about fake things, but real problems, creative problem solving, deep understanding, collaboration, and communication. The ELA can help you with math too. You know, the English Language Arts Common Core is calling for nonfiction, calling for technical reading and writing. Well, have the kids describe what they're doing. Have them document and analyze the kinds of projects they're working on. The White House and Food.org, everybody's all up in arms about programming. Well, how are we going to do that? Where's it going to fit in? If we try and make another segregated subject, we're making a mistake. It has to be integrated into math and science and English language arts too. I mean, people always stump me and they go, okay, well, how do you teach Latin with making? I'm like, well, you could, for example, program a Latin sentence generator. If you know how to use Scratch, you could make random word poetry. You can make, if you have to teach a computer grammar, you're going to learn the grammar better. I think there's lots of ways to do some really interesting projects in English language arts and history. And my co-author, Gary Stager, says great projects like hobbies have a self-regulating feedback loop. How do I know they got an A on bridge making? They did a bridge. And it stayed up, right. If they were all on the ground, it would not have, they would go back and try and build it again. If you're constantly in your students' feedback loop, if your judgment is the only way they're getting feedback, try and rethink about how to push that boundary. How to pick projects that drive down the necessity and the value of teacher judgment and create feedback loops where your projects are pushing up against the resistance of reality, where the LED is on or it's off. And you know what, if I've got one LED on, maybe I should add more. And then you have to figure out how. Every business expert will tell you that assessment in business only works if it mostly benefits the person being assessed. If you're working and all you hear is like at the end of the year they say, well, you failed. Well, how are you supposed to do a better job? What good does that do? You know, so in business they understand this. Now maybe they don't always do it, but I think we have to do more of the formative assessment, not real formative assessment. Now I know a lot of vendors have sort of stolen the formative assessment word and they've made it mean lots of little tests, but that's not real formative assessment. Formative assessment means it's being formed out of the work you're doing. You can do self-assessment like maker tables, like reflections. And really, I think we have to ask ourselves, are tests really assessing what we want them to assess? Do they really work? I think a lot of kids are being failed when they actually know how to do things, they just can't seem to get it out. We need to make the get it out the test, not a separate test. Now this is an example of documentation and reflection. This is an example of a maker table. So this is a before and after. You ask kids to describe or predict what they're going to do, write the steps down, and then you see, as they progress, can they describe things more accurately? Are there more steps and more steps that make sense? Can other people follow the instructions? And if they do this and it's useful to them, they will get better at it. So I want to finish up with some time for questions. But just to sort of wrap up, oh, the top is cut off. I think with these 4 variables in place, it really accelerates learning. So the 4 variables are a good prompt, appropriate materials, sufficient time, and a supportive culture including a range of expertise. Learners can really exceed expectations, including their own expectations. The nice thing about these 4 variables is it's really easy to tell. what's missing. If your kids are constantly running out of time and they just can't finish their projects, you need more time. You need to find a way to make more time. A supportive culture, kids have to be able to Google stuff. It's just time. The IT department, if they're blocking stuff, you have to push back on this. The internet is a place where answers are found. It's just the way it is these days. And how do teachers learn to teach this way? I talked about constructing modern knowledge a little bit in the keynote. We have a fabulous time. We have an alumni here of constructing modern knowledge. What was your project? Did you do the walking robot?
With Brian and Chris.
Yeah.
Yes.
So they tackled, the prompt was, make a walking robot. And like 3 really smart people, including you, spent like 4 days making a Lego robot walk.
And it was shockingly hard.
Yeah, right?
Shockingly hard.
Right. And teachers often, it far exceeds their expectations. People come in and say, I don't know anything about technology, I'm not a technology person, I'm just here to watch, and then 4 days later they're like down in the project bowels doing some really fun things. So I want to have time for questions. If you guys would like to talk about your own questions, we have about 5 minutes. Your own classrooms, your own experiences, happy to answer. I stunned you all into silence. It's lunchtime. That's what's going on. So anybody doing making in the classroom? Anybody got a maker space? Yeah? How's it going? It's in a library. I think the library is a perfect place for a maker space. I think you've got a lot of the kind of conditions for success. Cross-curricular, cross-grade. It's a hub already. I think libraries are brilliant places for maker space. Well,
it's a journey.
It's a journey. That's great advice. Thank you so much. It's a journey. That's worth to end on. Have a great lunch. And